No, I didn't. All right. This is aerospace engineering on, well, Thursday, February 25th, 2021. I'm going to try to explain basic orbital mechanics, the second skill. So the first skill is to be able to deal with circular orbits. The second skill is to be able to deal with elliptical orbits instead of circular orbits. So imagine that this crude sketch represents an ellipse. One of the things that Kepler figured out in the early 1600s is that all the planets in the solar system are actually traveling along elliptical orbits, not circular orbits the way we first imagined. And okay, truthfully, he didn't have enough information to work it out for all the planets, but he worked it out for Mars. And that was a big uh, enlightenment. And what he figured out is that when you have an ellipse, there's the center of the ellipse. This line I just drew is called the minor axis. Then there's the long length of the ellipse. That's called the major axis. And interestingly enough, half of the minor axis is called the semi-minor axis, and we represent that usually with the variable lowercase letter b. We don't care about b in our calculations. What we do care about is half the length of the major axis, and the symbol that we use to represent that is lowercase letter a. Now, don't get confused. You've seen letter A when I talked about physics, and we use letter A to represent acceleration. Here, letter A is a geometric distance, and it's called the semi-major axis. Semi-major, meaning half the long length of the ellipse, axis, lowercase letter a. What Kepler figured out is that the sun is not at the center of the elliptical orbit of Mars. Instead, there are two focal points in an ellipse. In a circle, there's only one focal point, and that's in the center of the circle. In an ellipse, the focal points are, let's say, crudely here and there. So there's two focal points, and the distance, letter C, I don't think we need to learn right now. I forget what letter C represents. Maybe the distance from the center to the focal point? That sounds right to me. So I think, but that might also be incorrect, right? I forget what letter C represents. Point is, haha, I don't care, at least at the moment. So here is a focal point, and here is the other focal point. For Mars going around the sun is at one focal point, and there isn't anything at the other focal point. It's just empty space. Or if it's almost a circular orbit, this would be still inside the sun, but there's nothing special about that. There's nothing placed there. So with the sun here and Mars in its elliptical orbit going around the sun, one of the laws that Kepler worked out is that when you are closest to the sun, you speed up and you're going really fast. In fact, there's a name for when you're closest to the central body, and that's called periapsis. Okay, so what is periapsis? Periapsis is like Greek words that means closest point in an orbit to the central body. And central body is the STK term for whatever orbit we're looking at. If it's Mars going around the sun, then the sun is the central body. If it's the moon going around the Earth, then the Earth is the central body. If it's a spaceship going around the moon, then the moon is the central body. So that's their generic term for what is the object that you are orbiting, whatever it might be. Could be Pluto. When the sun is the central body, then this is called perihelion, which means closest to the sun. When the central body is the Earth, we call it perigee, means closest to the Earth. When it's the moon, we call it perihelion, closest to the moon. And there might be a name already for when it's closest to Mars, but the generic name, if you forget, you could just call it periapsis, the closest point in the orbit as it goes around. So here at periapsis, your tangential speed is the fastest that it's going to be. And we would call that your speed at periapsis. I'll just put lowercase letter p. So v sub p is orbital speed at periapsis, no matter what central body you're orbiting. Nice. What Kepler figured out is that as you go away from the central body, the distance becomes greater and greater. The maximum distance, way out here, is called apoapsis. So apoapsis, also from Greek roots, means farthest point in an orbit, and yes, from the central body. And just like perihelion, you could call it apohelion, apogee, apollune, generically apoapsis. What happens is you slow down, and this velocity, which I'll call v sub, I'm debating, should I call it A or should I call it APO? Because I don't want you to get confused with average velocity. So for average velocity, I'll write AVE. Here, I'll just write one letter. V sub A is the orbital speed at apoapsis. All right. So, what do you know? We now know that even the Earth is in an elliptical orbit around the sun. And all objects in the universe that are obeying Newton's laws of motion, well, Newton's law of gravitation, are always in conic sections. You might remember the list of conic shapes from math class. There's the circle, where it's, a perfect distance, never changing from the central body. There aren't any natural objects that I know of that are in perfectly circular orbits anywhere in the universe. They just don't naturally exist. There's no particular reason why something would be in a circular orbit. By far, the vast majority of objects that you're familiar with are on elliptical orbits. So the Earth is on an elliptical orbit around the sun. The moon is in an elliptical orbit around the Earth. All the planets, all the asteroids in our solar system are in elliptical orbits. There are additional conic shapes. There's two more. There's a parabolic orbit, and that is where we sometimes see a comet coming in from infinitely far away, and it follows the path of a parabola, goes whipping around the sun, and then disappears off to infinity, never to be seen again. Those are kind of rare, but they happen. And finally, the last conic shape is a hyperbola. Right? So there's the circle, looks good. There's the ellipse. There's the parabola, not just from math class, but actual comets. And then finally, there's the hyperbola. Very, very rarely we will see a comet go whizzing through our solar system on a hyperbolic orbit. And what does that mean? How does it get there? That means its energy at infinity was even greater than zero. Or, in other words, it's as if it were thrown into our solar system, not just dropped into it from rest like a parabola infinitely far away, but actually thrown into our solar system, which means maybe it was whizzing by some star off in the distance and it had an interaction with the star that caused it to be whizzing out of that solar system at a high speed relative to encountering the edge of our solar system. So no aliens are really required to throw comets in our solar system. Now, based on this, there is this one guy who looked at a comet that passed through our solar system in the year 2017, and he said, "Oh, you know what? It's not actually following a conic path." How do you explain that? Well, the explanation would be it's exerting a thrust over time. And therefore, his conclusion is we were visited by an alien spaceship in 2017. I'm not making this up. This is current news because it takes time to analyze the data and get it published and stuff. So within the past few months, this claim was made. Before you leap to embracing that thought, comets are sometimes called dirty snowballs, right? So they have gas and dust coming out of them as they get closer to the sun. The sun heats them and they rupture little geysers on their surface. So an outgassing comet could end up thrusting itself into a non conic path. Maybe the object this guy studied was experiencing something like that. And since comets tend to rotate, just like the Earth rotates, that can cause the thrust to be in variable directions. Okay, so I don't know what to conclude about the spaceship who visited us. I personally think we were visited at a different time, but also in a comet. So there you go. What we care about is that you should realize, oh my goodness, there are calculations that could be done here. We might have to do, yes, you will, calculations where you have to calculate what is your speed here? What is your speed there? What is your orbital period? The good news is, if you were to consider the average distance from the central body, that average distance would be a circle, right? Okay, so let's do an example. Suppose I have an ellipse and the and it's around the Earth. So the perigee radius is something like 10,000 kilometers. So that's the closest you ever get to the center of the Earth. Keep in mind the Earth has a radius of 6,300 kilometers, so you're less than 4,000 kilometers from the surface of the Earth, but still, you miss the Earth. And let's say that at the farthest distance from the Earth, you're 30,000 kilometers. Well, here you're going fast, there you're going slow, but how do you do calculations you want to know? So the average is the semi-major axis. The average radius is the semi-major axis. And in this case, if you take the periapsis distance and add to that the apoapsis distance, divided by 2, in this case, I chose nice simple numbers. The average distance from the Earth would be 20,000 kilometers in this example. And from that, you can calculate the average speed using square root of gm over a, the semi-major axis. I remind you that if it were a circle, it would be gm over r. It would be a single value. So the good news is, even though it's elliptical and it's speeding up and slowing down, the average speed is based on the average distance. And that average distance is the semi-major axis. How do we get that? The periapsis distance on this diagram would be the distance from here to there. That's our peri. The apoapsis distance is the distance from here to there. That's our apo. And here I wrote APO. If you add these two distances together, then you go all the way from here, all the way to there, and this distance is 2a. So if you add the periapsis distance to the apoapsis distance, and then divide it by 2, you get the semi-major axis, the average distance. Ta-da! Of course, now there's going to be equations for calculating parameters. So the good news is the orbital period is t squared equals 4 pi squared a cubed divided by gm. Meaning the orbital period is the same as the period of a circular orbit with a radius equal to the semi-major axis of the elliptical orbit. Elliptical orbit. So example, our peri equals 10,000 kilometers. Our apo is 30,000 kilometers. Semi-major axis is 20,000 kilometers. And standby. Okay, so I've taken the trouble to write a program. No doubt you students want to write your own that does this sort of stuff. So I've written a program to work with elliptical orbits. Sorry for the dirt. Okay, so what is this program called? I wrote a program called Orbit. And let's set the central body to be the Earth. And let's do a circular orbit with a radius of 20,000 kilometers. Here you can see the period would be 7.8 hours. Your speed is 4,464 meters per second. Should I write that down? So circular orbit has a period of 28,149 seconds, and the average orbital speed was, well, not average, the only value. The orbital speed is 4,464 meters per second. Okay, so if instead of a circular orbit, I had an elliptical orbit, and I wrote my program where I can either put in the periapsis distance in the period, or I can put in the 2 radii, or I can give up and return to the main menu. I'm going to do the 2 radii. So the periapsis radius we said was 10,000 kilometers. The apoapsis radius was 30,000 kilometers. And thanks to the laws of physics, here's what you need to be able to calculate. For example, the periapsis altitude above the surface of the Earth, the apoapsis altitude above the surface of the Earth. Note that the period works out to 28,149 seconds. Ta-da! Matching 28,149 seconds for the circular orbit. The periapsis velocity is a big number because you're going fast. The apoapsis velocity at the bottom is a small number because you're going slow, but the average velocity, 4,464 meters per second, ta-da, matches the circular orbit of 4,464 meters per second. So dealing with elliptical orbits, the new calculations for you to master deal with how do we find the speed when it's going its fastest at periapsis? How do we find the speed when it's going its slowest at apoapsis? And you might be wondering, well, what about all the rest of the time on the elliptical orbit? What about when it's here or when it's there? What about there? And the good news is we don't care. I care in my research. I've been building a space transportation system that always uses periapsis and uses a region near apoapsis, but not at apoapsis. And so for my research, yeah, I have to worry about what is the speed and direction of this object when it's not at apoapsis. But the good news is I'm not going to torture you with doing this research level calculation. You need to only worry about what if I'm at apogee. So we're only going to be concerned with the two extremes of the elliptical orbit. Fastest point, slowest point. Okay, so how do we calculate the speed at its fastest point? Why, there's a formula for it. The speed at periapsis is equal to the average speed, and now you know how to calculate that. You find the average speed by finding the semi-major axis and treating it as if it were a circular orbit. There's the average speed. If you take the average speed and you multiply it by the square root of, oh my goodness, the apoapsis radius divided by the periapsis radius, you're done. That's the whole formula right there. So in this example, if I go 4,464 meters per second, and I multiply that by the square root of 3, whoa, where did I get 3? I just reduced 30,000 divided by 10,000 is 3 divided by 1. So if you were to get out of this program, quit, and then multiply 4,464 times the square root of 3. Dun, 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 dun. Oh, I didn't write down what the other values were, did I? Oh, well, based on short-term memory, I get 7,732 meters per second as my apoapsis velocity. So I've written that one down. Of course, there's another equation. That is, how do you find your speed at the slowest point, at apoapsis? Well, the formula is the flip of this. So your apoapsis velocity is the product of your average orbital speed times the square root of your periapsis radius divided by your apoapsis radius. So if I divide by the square root of 3, instead of multiplying by the square root of 3, 4464, divide by square root, square root of 3, enter. I claim that was the other speed, 2,577 meters per second. Ta-da! This ends the recording.